All right, I guess we're going to go ahead and get started here. My name is Jacob Rapp, and I work for Cisco, and we're going to be talking about the data center and Hadoop. So as far as the agenda, what we're going to be going over today is first we're going to look at some Hadoop considerations, traffic types, job patterns, network considerations, compute considerations, and look at kind of what's happening in the data center when you add a Hadoop cluster to it. Next, we'll look at some network integration. Cisco being a network company, we've done a lot of benchmarking, we got a lot of data from some of our own clusters that we're running, and looking at what can we do to integrate with the network a little bit better. We're talking about coexisting with the current network infrastructures. And then we'll be talking about kind of like the big buzzword of the networking industry today, some software-defined networking things, but kind of making it kind of more open and programmable. And the goal is to get to the point where it's all application aware, so that as you look at some of these distributed applications like Hadoop, you really have to take into account all the different pieces of the infrastructure or of the distributed system, which the network is a core component of, as well as the compute, as well as the application, everything, the disks, the memory, the CPU. How do they all combine? How do they work together to create the most efficient system? And then again, then we'll follow up on some multi-tenancy. So as you're running more things on top of HDFS, or if you're coexisting your HDFS and MapReduce and HBase and other things, like just maybe a relational database under the same infrastructure, what challenges do you run into? And how can we overcome these types of issues? So first of all, some of the job patterns in Hadoop. So as we look at some of the benchmarking we did, we took a look at a few different job patterns. So we start out with, say, an analyze type job, where you start out with, say, quite a bit of ingress, quite a bit of data to start with. Just like for a really basic example, word count, where you're starting out with a book. And you're kind of narrowing down as the mappers are finishing, kind of like finding how many A's or thes or counts or whatever words are in the book. It's kind of narrowing down, then you're finally shuffling that data, and then it's kind of narrowing down even further as the reducers are running on that data. So your traditional like business intelligence type jobs kind of fit this model, where the key point here is the reducers, when the reducers kick off. Because as the reducers are kicking off, and you're shuffling the data, that's the amount of data you actually have to get across the network. So yeah, you try to do a pretty good job at the beginning for the map tasks to kind of run everything local where the data is, but after I'm running my maps, and I got to send this to a reducer somewhere, so it goes across the network. The ETL type jobs, where you're kind of just transforming data, you're sending the entire data set across the network in your shuffle. So you're starting out with a certain amount of data, your mappers are running, shuffling to the reducers the same exact amount of data. Start out with a terabyte worth of data, you're moving a terabyte worth of data across the network. And finally, there's some explode, which is kind of, I don't know, maybe a little bit less out there, but it's even worse, right? You're starting out with the computation, you're kind of adding on top of it, and you're basically shuffling even more data than you started out with, which is even a worst case scenario as far as network traffic goes. So how do these traffic, as we're running a job, a Hadoop job, MapReduce job, what kind of flows are out in the network? What kind of flows are going across the data center fabrics? You really start with, you have some small flows, your messaging, your heartbeats, anything that's kind of like latency sensitive. And this could include flows in the data center that may not be part of Hadoop. They may just be another traffic that has latency sensitive characteristics to it that is flowing across the same network infrastructure that you have, say, a MapReduce job running on it, or some replication or data ingest coming in. But there is these mouse flows out there. Then you have this kind of small, medium, what we call incast. Incast is basically a many-to-one type scenario. Anytime you have many senders sending to one receiver, you have what we call incast. And I'll go over a shuffle is a pretty good example of your medium incast data. You have all of these map records that you're, or the map values that they're shuffling across. So they're not they may not be that huge of an amount of data, but it's coming from a lot of places at the same time. then you have these large flows. It may not be an incast flow, but it's just a large flow in general, maybe an HDFS ingest, any type of flow that's really long-lived in the network. And then finally, the large incast. So anytime you have really large flows that are all going to the same place at the same time. And an example of this is the replication. So as replication starts kicking off, a single node may be getting replication copies from various different nodes in your cluster all at the same time. So if you combine these all in a Hadoop cluster, you kind of have like this kind of diagram here of what the traffic patterns start to look like in a particular MapReduce job. And I think the key challenges that we're going to be talking about even further is that, okay, great, now we have this cluster. We don't want it to be kind of siloed off in a corner by itself. We want it to integrate into the mainstream data center architectures. So how does this affect other traffic? How does this affect multi-tenancy, multi-applications, or even just multiple things running on top of HDFS? Maybe you want to start thinking about co-locating an HBase cluster with MapReduce. So what does this look like from the network perspective? So this graph is kind of hard to read. We have all this stuff online and actually a better format. I'll give some links out there so you can kind of, if you really want to look into these things in detail. But what these graphs are basically showing is this is looking at a single node in a cluster. We ran this on, I think, about 120 node cluster in this example. And it's basically a single node and what data it's receiving. So this is looking at like all the RX data, received data on that given node during different types of jobs. So the first one is, say, just a simple word count. All of these have the same amount of starting data. So we started out with several terabytes worth of data to start with. And they all are running the different types of jobs on that particular data. So the first one, you can kind of see in a business BI type job, your mappers are kind of spread out. Your map is actually doing the majority of the work in this case. So as your maps are running and finishing, it's shuffling data periodically through the network. So the reducers on this node are periodically just grabbing data from the maps that are finishing, but it's happening throughout the entire job as it's running. And then you have, say, an ETL type job, where we're using, in this case, Terrasource. This is not really an ETL job, but it's kind of almost worst case scenario in some of these networking traffic scenarios. So basically, we ran it twice, one without output replication on, and then again with output replication turned on. So as we look at this, what you can see, even in a better examples, like say this bottom example, of really what the incast type of traffic is happening. So in the very first bit of information right here, so what's happening in these graphs, these red lines are the aggregate amount of traffic coming to this node. All of these small dots down here are nodes in that cluster that are sending to this given node. So as you can see in the shuffle, you have a lot of small dots down here that are making up this aggregate peak. So the reducers on this given node are receiving a bunch of data from the shuffle. And actually, in this case, you can actually see a locality miss at the very beginning too, where this particular node didn't have the data, so it had to go grab it. So that's why you see this initial spike right here on this particular graph. But then you have this output replication where it's somewhat difficult to see, but you have these small dots. All these small dots higher up the stack coming from fewer places. So this represents the large incast. You have, say, 128 megabytes or 512 megabyte block size. That's how much data you're sending across the network. So it's coming across to this guy in multiple chunks all at the same time throughout these types of jobs. So we'll get to why this is fairly interesting. It's interesting to understand, just to understand the characteristics of a cluster, but what now? So great, we have this data. What do we do with it, and how can we take advantage of this information to make life operationally and more simplistic, and have a Hadoop cluster run quite a bit better? So integrating into the data center. As we ran a full study on this, we actually presented a lot of this data last year's Hadoop Summit. So there's actually a whole paper that we wrote on all of these particular attributes and why they matter in a data center design. So I encourage you to look online. I have a link, but I'll go over a couple highlights in this before I get to some of the deeper integration and some of the work we've been doing over the past year in this space. So what we found out, I mean, in the enterprise is a bit different than, say, some of the larger Hadoop clusters out there. So if you're running thousands and thousands of nodes, say you have 50,000 nodes, you're probably in a different place than if you're running a couple hundred nodes or 500 nodes or even 1,000 nodes. There's different orders of magnitude, but what we found out is the availability in the general enterprise is probably the #1 effect of performance on a given cluster. As links fail, as nodes fail, say I have only a couple racks of servers. One of those servers goes out, you have a fairly large problem, especially if you have, say, 12 2-terabyte disks on that given cluster. You're basically all of a sudden that one node goes out. I need to re-replicate everything to keep my replication, like say factor of 3 or something, in place. So all that 24 terabytes of data that was on that given server, I now need to go replicate across the network, and this causes this big storm of traffic that's going over this Hadoop cluster. And this is where you kind of get into some of the link aggregation characteristics that you can kind of design into the network from a server, having multiple links up to the different top-of-rack switches, kind of like the redundancy type models that you can go deploy to avoid some of these scenarios. Because the last thing you want is a top-of-rack switch going out, you lose 1 rack out of 3 racks, you're probably in a pretty bad place in the given cluster. It may not be even usable at that point. Buffering, I'll go into in a lot more detail in a second. Oversubscription ratios, node speeds, and then finally latency. So latency is an interesting one. I don't have a bunch of details on here I've gone over in the past presentations that I've given, which are actually all on the Hadoop Summit site from last year. But basically, latency itself wasn't a big contributor to performance. Like having the lowest latency out there wasn't really changed anything. But latency is important to understand in terms of buffering. So if I start racking up a lot of buffering on the network, how is that affecting other applications out there? It may not be affecting, like say I'm replicating data across the network and I'm buffering some. It may not be that big of a deal for the replication. But is that going to affect other latency sensitive traffic on the network? And the answer is absolutely yes, and we have a couple examples of it moving forward. One quick thing to touch on, Hadoop can and will eat up 1 gig, depending on the job, but 1 gig utilization's gone, 2 gig utilization's gone. 10 gig is really where we're at with Hadoop and in Hadoop environments. Will it run? Yes, at 1 gig. Very effectively, no. You'll have quite a bit performance degradation when you're capping out this utilization like this. So 10 gig dual 10 gig is kind of the status quo at this point when designing new greenfield Hadoop clusters or when thinking about upgrading your Hadoop clusters into something new. 10 gig is there, and it's a reality today to the server, not just the uplinks, but to the server. And if you look at most modern switches today at the top of rack, you'll see that most of them have 10 gig, and then have 40 gig uplinks. So the move to 40 gig is happening drastically, really fast in the industry right now as far as uplink speeds. The move from 1 to 10 was actually fairly slow in orders of magnitude, but it turns out the economics of 40 gig are actually turning out to be quite a bit better than the economics of 10 gig. A single 40 gig interface is a slightly different form factor than what a 10 gig interface was. It's in what they call a QSFP format in generally, where 10 gig is in SFP, like small form factor pluggables versus the quad form factor pluggables. And it actually turns out that one of these interfaces is basically cheaper than 4 10 gig interfaces, because it's kind of an evolution from 10 gig. So it's actually, the adoption of 40 gig is going to happen at a drastically faster rate than 1 to 10 gig took place. This is just an example of the dual attached versus single attached servers. I kind of went over that, where if you dual attach your servers to a top of rack switch, you lose a port, you affect the job drastically as that failure happens. Where if you have dual attached servers, you're not going to kind of see those types of failures. And then buffering. So this is where I was kind of hitting on the points of 1 gig versus 10 gig as well. So as I'm overutilizing the link into the server, like I showed in the previous graphs, where 1 gig is utilized, it's going to back up somewhere. So first hop is going to start backing up on the switch. And then it's going to start dropping packets eventually, and then it's going to start backing up to the next hop, and then all the way back, and then TCP is going to rate limit, and everything's going to start like slowing down considerably when you're looking at the 1 gig performance. 10 gig alleviates that quite a bit, but it doesn't solve the problem. I mean, adding a bunch of buffer to a switch, I know you'll see probably some vendors advertise, I have a 10 gig or a 2 gig worth of buffer on my switch. You'll never run into a problem. But that's a problem in itself. There's actually this well-known thing in the industry called buffer bloat, which is a big problem in general you're just throwing buffer at a problem, but you're not solving the problem. You're not fixing the problem. You're not looking at the symptoms of the problem. You're just saying, okay, I'm just going to add more buffer when I probably should have gone to a higher speed link or made other measures. And that's the whole like day worth of talk by itself, because there's things to fix TCP and things like data center TCP or ECN, but those are kind of like longer conversations in the industry right now. Some of the findings, I have the link down here at the bottom. If you go look through this, a lot of the findings and a full paper on this is available online, and from my recording from the last Hadoop Summit as well, on really a lot more details that I went over in this reference architecture. But what I wanted to spend quite a bit more time on is how we integrate into the network a bit more. So this is what, on a given switch, a network admin sees. So I do a show interface, or a show interface brief. All I see is Ethernet interfaces. So I see here's my ports on that switch. Here's a VLAN maybe, whether they're up, and what speed they're running at. And then I go one step further. There's more than just this on the box. So MAC addresses, great. So I go look at counters, I go look at that, and then I go punt it back to the application team and says, if something goes wrong, here's my MAC address of the server that I'm looking at. Can you go, I'm dropping packets or I'm doing this, go examine what's happening. But we can be a little bit smarter now. Most of these switches out in the industry right now and at Cisco are programmable, and you can make them application aware fairly easily. We spent some time writing some scripts. So we can write Python scripts in C or anything like that. We can open up sockets, we can pull in information. We can do a lot of things from these switches now. We don't want to do everything though from these switches, and I'll get into that in a second. But from an operation and troubleshooting standpoint, it is really interesting to add some more value and make these switches application aware. So what we did here is that we just did a simple port server map. So we took those MAC addresses and we populated them with names of the servers. So instead of seeing Ethernet 1.1 and a MAC address, we now see the actual name of that server that was on that switch. No, in this case, there was nothing on 110, so there was nothing connected in there. And then we can kind of go a step further. So we can look at a tracker list, like a task tracker, and which server ports are connected in that given, on those given nodes. And then one step further from that, we can see a buffer map. So where I was talking about before, what's causing buffer, what's causing congestion, I can make simple outputs, say, okay, here's the server, here's the buffer. Okay, and here's my high-level view of what's happening on the switch and what's happening on the network. Then I can actually even drill even down further, which I can look at jobs and which jobs are taking up the most buffer on the switch. So now when the network admin's looking at this data, they're just saying, okay, well now I know, I can give, when I'm troubleshooting something, I actually know here's the job, here's the amount of buffer, here's the interface, here's the server, all in one easy output moving forward. And I'll talk about how we did this in a second, but this is kind of the stuff that we can start moving onto the network and start pushing on the network. So we're no longer just kind of punting things over the fence to each other as the different teams kind of say, okay, is it your problem, is it my problem, how do we troubleshoot this? Everything becomes a little bit more intelligent as we start moving forward. And then again, we can also look at historic views. So we actually can keep this data on a flash drive on the, or internal flash, or even some of the new switches have solid state drives in them. So we can now just start dumping these statistics onto a disk as well and start seeing historic records. And this kind of goes into the next point that what do we do from there? So normally when you're looking at monitoring a cluster, you're looking at CPU utilization, maybe you're looking at bytes in, bytes out of the server, you're looking at established connections, but there's a big hole that's missing in when you're looking at managing a cluster. And that's really the max buffer usage. So what we can do with those statistics now that we gathered on the switch, there's kind of a new model that's emerging within networking and giving statistics. You can almost picture a switch as just a big sensor. It has a lot of data on it that we're not really correlating very well today. So we now give these scripts where we can pull things at an incredible interval on the switch itself. We could run this Python script in the background on the switch, pull all this buffer information, aggregate it, and then export it out to a server that's your monitoring workstation every minute, every hour, et cetera. So now you have a historic view and a look at actually what's happening on the switch right next to all your other graphics and all your other graphs of what's happening on the given server and what's happening in the given cluster. So now you're not just looking at, okay, yeah, my CPU spiked here, and then I was sending a lot of traffic at that given time, I had a lot of connections, but then I now know actually, oh yeah, during this whole given sequence of time, I was actually buffering quite a bit on the network too. So when I'm looking at performance of a cluster, what's happening, I can now I have a bit more complete picture of what's going on. So say performance of one job wasn't very good or something happened where it affected a different application, I can go now troubleshoot this a lot better and understand what's happening to a great more detail. And then we can now create these nice graphs of exactly what's happening within the network and what's happening during the job. And what basically this graph is showing is that this is the maps finishing, the percent they're finishing. This is the percent the reducers are finishing. Here's the network traffic that's happening, whether it's a shuffle or replication type traffic. So now I can kind of go into the logs. I can get all the logs from all the servers and correlate what's exactly happening throughout this cluster at any given time. And then I add in the buffering on the network as well. So maybe now I can kind of find out what was actually causing the performance. I know what job, I know what flows, and I know what type of traffic was actually causing this performance degradation or what was happening on the network. So the question is, why does this really matter? So great, I got this information, now what do I do with it? Is there anything meaningful that I can really get out of it? Now great, I know I'm buffering, what do I do about it? So that goes into a quick talk on multi-tenancies, or multi-tenant environments, where you can basically have, there's different types of multi-tenancy that people talk about. I'll talk about the two bottom ones first, which are the job-based and department-based. I think these are really handled by schedulers, right? I mean, if it's a job-based prioritization, a scheduler can really handle that fairly well. Same thing with department-based. There's permissions and scheduling and those types of things that can really address those problems. But what happens when I combine two applications together? So an application multi-tenancy, so Hadoop plus HBase, for example. Say I want to co-locate these things in the same cluster. What do I need to know when I'm doing this, and how do they affect each other? So here's the different types of traffic now. So now I have these really critical my reads and updates that there's maybe an SLA on my reads. how do I make sure that those are met? And that traffic doesn't interfere with the elephants that are stampeding on the bottom and the replication. Because if I'm replicating data and it happens in a minute or a minute and a half, it may not be that important. But if my reads spike over that same period of time, that's maybe direct user experience issue. Because I think there's some studies on, I don't know for who was talking about it earlier today, on the people feel that the machines are in control of them if there's a delay. The quicker I get this information back, the more the user feels like they're in control of things. So you start seeing these blips in user experience, that's when you start seeing the alarms and you start getting people complaining. And another thing we actually talked about back in actually at the Hadoop World in November of last year, we actually looked at what we could do with this data. And we said, okay, well, what's a problem? So let's start with a problem rather than saying, hey, I have this nifty gadget and I can go solve the world with it. So one problem was in HBase, there's this major compaction event that happens. And some customers were noticing that there's a spike in traffic, spike in read latencies during this major compaction event. So we actually started correlating data. We're like, okay, let's add the network data in there, let's add the buffering, let's all correlate these in a nice graph and understand what's happening. And what we actually found out is that during this major compaction event, there was a large spike in buffering that was happening. And we actually traced it back to the flows of, they were the actual major compaction flows that were causing buffering. But what was happening, the reads were just getting backed up in that buffer as well. They didn't cause the buffering, but they were affected by it. So what we did was so that's kind of where you see this big spike up here in reads. So what we did is on a switch, we can do a simple quality of service policy where we can prioritize one given traffic type over another. So we said, okay, well, let's give I mean, I don't care if the major compaction takes a little bit longer to do as long as I'm not affecting my reads. So I prioritized my reads above the major compaction event, and I was able to drop the latency actually 45%. So I actually stayed pretty flat. So it actually turned out the network was one of the issues when that was causing these reads to be spike. So this is just an example down here. The buffer here, this is the major compaction event, and then this is the showing that we actually ran YCSB on this for the benchmark, and it was buffering nothing. There was no buffering happening at all. So that's why we were able to get that latencies down. And same thing so in this case, we looked at not just HBase itself, but what if we kick off a MapReduce at the same time we're running the same cluster? So say we're running HBase with MapReduce on the same exact cluster. What happens? So this was even worse. There was this massive spike when we kicked off the buffering in say Yahoo TerraSort benchmark when we're running YCSB on the same cluster. There was this big spike in latency again. So the same quality of service policy that happened, we were able to get about 60% read improvement on those given clusters. So I did have another slide and an updated deck, but I guess it didn't get updated. But we actually have these scripts on GitHub /data center where you can actually, all the examples I did are all it's all open source. There's nothing to pay for. You can kind of go download them and understand exactly what's happening on the network. But how do we do it is what I want to talk about in a little more detail with the time that I have. So basically what we do in the network, there's an optional step. Some people choose to do it and some people don't. It's all about time synchronization. So most of the time you synchronize things with NTP. It synchronizes fairly well, but we're quickly finding that it's not really that accurate. So there's a thing called Precision Time Protocol, or IEEE 1588, that's starting to become widely adopted out in the industry. So this is where you basically have, you're synchronizing everything to GPS. So you have a GPS unit on the top of the data center, and you have a grandmaster clock that is then synchronized everything through Ethernet. So I basically push things down, push the signal down to a switch. The switch itself has a pretty high precision oscillator that's keeping track of that time, and then disseminates the clock down to all of the servers that are then synchronizing to the hundreds of nanoseconds level to really closely correlate everything. You don't need to do that because it's still fairly close correlation, but if you really want to correlate everything, that's an initial step to do. The second piece is when we look at, let me go back to this example up here. So when we look at like this type of information, how do we get it? All right, so basically if you go to the GitHub site, we will have some examples on there on how we got this type of information. Basically all we're doing is either through an API, if it's available, or basically just opening up a connection to the server that has this information. We're going and grabbing it and basically correlating it into a nice output with the data that I already have on the box. So I have this buffer information already. I have a port information. Now I just keep adding on top of that. It's actually pretty simple to do. I think it only took a week or two to actually build this script and debug it and all those types of things. But it's something that's readily available now, and we can now start correlating these applications. And then from getting these types of information, we're just pushing that data out. Like I talked about before, that model of just push. Right? I mean, we have things like, and if you if you know the networking industry, there's a thing called like SNMP to kind of go pull data in. But we're quickly finding out it's fairly inefficient to do that at any granular level. So I don't really want to go, say I want everything say I want a counter every 1,000 times every second. I don't want to make a request 1,000 times every second to try to go grab that information for every single counter across the network, for every single network device across the network. It becomes hugely inefficient to go do. So now what we now can do is use these same Python scripts on the switch to basically run a monitoring suite. So you can kind of go grab every single counter on the box at a really high granular detail, dump it into a file on the system, and then push it out every minute or every 30 seconds. So now I have every 30 seconds or minute or second a huge granular detail of information to create these log files out of. And with that, that's generally what I have for the presentation. If you want to know more about specific products we sell, we have that information here too. From our switching, servers, and automation tools. So any questions? Yeah, it was so the question was with the graph of 1 gig, 10 gig, 2 gig, et cetera, was it the same load? And the answer is yes, it was the same exact job. All we did was, and the same exact cluster too, all we did was just switch out the NICs to be able to, whether it's 1 gig land on motherboard or 10 gig NICs in the server. But yeah, it's the same exact. Yeah, I think that's, so the question was, is that say you have a large cluster, multiple racks, multiple server switches, how do you know which ones are actually causing problems? So I think in these scripts, these are just example scripts, they can really simply be modified to set alarms or thresholds. Say, I can baseline everything to say this is my normal operation, and then anything 10% or 20% above that baseline, I can then set thresholds and alarms to kind of send information or send emails or send notifications out if something fails. I mean, it's a full suite of Python. I mean, you can import whatever classes you want or libraries you want and do whatever you want with it. No, there's no graphical interface. That's one of those things of, some things are better off done elsewhere. Know what's core and what's not.
Could you go back a slide? So in the QoS picture, How do you differentiate the read traffic from other Hadoop traffic? Because both of them are application level traffic.
Sure.
And to give high priority to the read, you have to know that that flow belongs to read and the other flow belongs
Sure.
to, let's say, some low priority
Sure.
job.
Yeah, I think in this case it was a little bit more straightforward than some other cases that we've looked at. For this case, it's a client is generally reading, not a node, and it's not a region server doing a read or a backend HDFS server doing a read. It's a client doing a read that's expecting something back. So I know what's a region server and what's part of my HDFS nodes. So basically any traffic that's not going between those is probably something I want to prioritize because it's going to a client. So it's based off of like either IP address ranges or TCP ports. I think the more some more harder things to get to is that things going between, like say in a MapReduce job, how can I prioritize a shuffle versus a replication? So those things you actually have to get down to like the TCP port level of, I mean, that's actually, Hadoop does a good job in terms of logging what's happening and understanding, okay, well, I'm now shuffling this much data to you, or I'm replicating this much data, and here's the TCP port number that I'm using. And on switches, you can actually put in rules that are based off of TCP port numbers. I mean, other alternatives we could do that we've been looking at is whether you can do that on the application too. You can tag a given packet with a given priority, but that requires going into core MapReduce code and going to change things versus just kind of doing things status quo and not having to go muck around with the code itself.
Thank you.
Anything else? All right, well, we'll be around. I'll be around all day and all day tomorrow. If there's anything else, I'll be at the Cisco kiosk. Thank you for your time.